Welcome again. Today we are going to talk about non-parametric tests. I will start with a quick reminder of what statistical test is about. You start with a null hypothesis. Usually it means there is no effect, no difference between your biological conditions. You set your significance level. You do perform your experiment, collect data and find a statistic T, observed statistic. Then you put this observed statistic in a context of the null distribution. It cuts off a certain probability. This is your p-value, and depending on whether p-value is less or greater than your significance level, you either reject the H naught or you simply claim that there is not sufficient evidence. What does it mean, non-parametric? What are non-parametric methods? You are familiar with parametric methods. Parametric methods require finding a parameter or parameters, for example, mean, standard deviation, standard error. The example of parametric test is a t-test where you compare two mean values, and also you need to know standard deviation for this. Parametric tests are sensitive to distributions. If there are strong outliers, if your distribution is very far from normal, a t-test will not work. Parametric tests are also more powerful. That means that they can detect a smaller effect size at the same significance level. Non-parametric methods, on the other hand, are based on ranks. The figure in the right shows you the same data as in the left, but instead of values, we show ranks. We pull all the data together and we order it from the smallest to the largest. Non-parametric methods are distribution-free if they don't care what your data are distributed, and they have wider applications, but again, they are less powerful. We start with Mann-Whitney test, which is also known as Wilcoxon rank sum tests. Some of these names are a little bit of a mouthful, unfortunately. This test is a non-parametric alternative to a t-test. In Mann-Whitney test, there are two samples representing two random variables. I'm going to call them X and Y for the purpose of this definition. And this is an example of data. This is a lifespan of mice. There are two strains, wild type and a knockout. And you can immediately see that these data are not normally distributed. There are strange things happening. There are some mice that had lifespan of 0. They died very early. The null hypothesis in Mann-Whitney test is that there is no shift in location and or change in shape of our data. We can write it down as this, that probability of X being greater than Y is the same as probability of Y being greater X, and it is a half. You can understand this in terms of two populations. You draw a number from population X, you draw a number from population Y, and you compare them. Now, if the null hypothesis is true, and now you repeat this draw again and again and again, X will be larger than Y 50% of the time, and Y will be larger than X 50% of the time. There will be symmetry between these two data sets. This is how we carry out the Mann-Whitney test. We have two samples of numbers, and for each X, which is a value from the first sample, we count the number of Y's, such as X is greater than Y. In this picture, we look at this particular value X, and all these Y's that are less than X are marked here by blue lines. The Y's that are greater than X are marked with orange lines. And the number we find for this particular value is 4. There are 4 Y's less than this X. We repeat this for all X's. We repeat this also for all Y's, and we add up all these numbers. We find UX, which is 10, 2 plus 4 plus 4, and uy, which is the sum of all these numbers. The test statistic is the minimum out of these two numbers. In this case, it is 10. This picture should help you understanding how this works. U, the statistic U, measures difference in location between two samples. Imagine samples represented in this very simple diagram where all x's are greater than all y's. There is no overlap between these two samples. The statistic U is 0. Specifically, UY is 0 because all y's are less than all x's, while UX is at its maximum. Now imagine that we add a constant to this sample y and shift it up and up with respect to the sample x. What happens is that at some point there will be y's which are greater than x, so uy will go up and ux will go down. Somewhere in the middle, these two curves will cross. That means that there will be the same number of x's greater than y's and the same number of y's greater than x. This is a symmetry. This is some sort of an equilibrium between these two samples. And if we continue shifting this sample up, we will end up in a case where all y's are greater than all x's. Uy reach its maximum, ux will be 0. Our statistic, U, is the minimum of these two samples. This is what it looks like. It reaches a maximum here when samples are most similar. As usual, we build the null distribution. We have a population of mice. I don't specify the mean or standard deviation. I don't even specify the distribution here. It doesn't matter. This is a distribution-free method. We select a pair of samples of size 7 and 6, just like in the original experiment. We find U and repeat it many, many times and build a distribution of U. It is shown in this figure. And you notice two things. First of all, this is a discrete distribution. U is a count, so it is an integer number. And secondly, it looks a bit weird. It looks like only half of the distribution. This is due to the way U is defined as the minimum of two variables. This distribution can be well approximated by the normal distribution, or at least this half is approximated by the normal distribution with a known mean and standard deviations. We can have equations for this. So that means we can cut off and calculate probabilities in this distribution. As usual, we take our observed statistic, which is 10, and we put it in the context of the null distribution, and we calculate the tail p-value, which is 14% in this particular case. Mann-Whitney test does not work for very small samples. Imagine you have two samples of size 3. There are 3 numbers here, 3 numbers in the knockout. The problem is, because this test only checks where the numbers are greater or less on each side, there are only a few possible combinations of x and y. And actually, there are 5 possible combinations, and it gives you only 5 possible p-values, as shown here. 5 values of the U statistic and 5 possible p-values. And if all y's are greater than all x's, the p-value would be 0.1, which is completely useless. It won't give you any significant results. Mann-Whitney test requires larger sample. I would suggest at least 8 or 10 points in each sample before you use Mann-Whitney test. Mann-Whitney test is a non-parametric version of the t-test. How does it compare to t-test? On the left, you see our lifespan data. The mean and standard error are shown here. This is what the t-test does. And t-test returns a p-value of about 4% here. However, there is a problem with this approach as lifespan data are obviously non-normal. There is a group of mice here with shorter lifespan and 2 of them where lifespan is exactly 0. These are outliers. So t-test will be strongly affected by these outliers. The Mann-Whitney test is based on ranks, and the right-hand panel shows only ranks, not actual values. And this test provides a p-value of 0.14. Mann-Whitney test is good when you have weirdly distributed data, like some sort of a score. This is a score from a proteomics experiment, and the distribution of these scores, as you can see, is non-normal. There are tails here which are stretched into higher values. Even better, perhaps, Mann-Whitney test is used to human-assigned scores, like Apgar score, which is used to describe health status of newborns. Because this score, Apgar score, is completely arbitrary, it is hard to say, for example, whether 6 is greater than 5 by the same amount as 5 is greater than 4. We don't know the distance between individual score values. We only know which of them is greater, which of them is smaller. This is the so-called ordinal value. And this is where Mann-Whitney test is very useful. This example comes from a new prenatal care program in some rural community. And the usual old and prenatal care program, the scores received were like this. And then under the new program, they were increased, they were improved. And we can use Mann-Whitney test to compare the old and the new program. And p-value here is 3%, telling us that the new program is indeed better than the old program. This is how you do this in R. You provide with two vectors of data, and you do a Mann-Whitney test by calling a function Wilcox.test with these two vectors. The Mann-Whitney test compares medians if both samples have similar shape. If shape is different and you still want to compare medians, you should use a mood test, which is slightly different. I only mentioned this on the side. This is the summary of Mann-Whitney test. The input for the test are two samples. Values can be ordinal. Assumptions are that samples are random and independent, which means there is no before and after data. And it is used to compare location and shape of two samples. The null hypothesis is that there is no shift in location and or change in shape of data. The stronger version of the null hypothesis is that both samples come from the same distribution. It is also known as Wilcoxon rank sum test. This is an alternative name. This is the non-parametric counterpart of t-test. It is less powerful than t-test. If your data are normal or roughly normal, you should use t-test instead. And it doesn't work for small samples. It also doesn't give you really any effect size. U is not a very good statistic to tell you how different the samples are. The names Mann, Whitney, and Wilcoxon come from these three gentlemen. Frank Wilcoxon published his first paper on this test in 1945, and then Mann and Whitney, 2 years later, they published a test showing an improvement of the original idea. Hence, this test is usually called Mann-Whitney test, but sometimes it's also called as a Wilcoxon test. The next test is a Wilcoxon signed rank test. These names are a bit of mouthful. The previous test was called Wilcoxon rank sum test or Mann-Whitney test. That's why I prefer to call it Mann-Whitney test, just to make a clear difference. This one is Wilcoxon test. It's a non-parametric alternative to paired t-test. Again, we have paired data. This is our old example of obesity study in mice, where there are mice before and after treatment, and we record their body weight. The null hypothesis in Wilcoxon test is that the difference between pairs follows a symmetric distribution around 0. We don't care about the mean or standard deviation here. We only ask about how they are distributed around 0. This is how you perform this test. We find absolute difference for each pair, and we also find the sign of this difference. Orange lines show the sign of +1, Blue lines show the sign of -1, where mice either increase or decrease their weight, respectively. Then we order and rank all these pairs according to the absolute difference and create I, which is a rank of a ith pair. The test statistic is the sum of Si times Ri. Okay, this is probably hard to understand. Have a look at the actual example in data. These data shown in this plot are reproduced here. This is all the axis, this is all the before data, this is all after data. This delta I is the absolute difference, which is a difference and take an absolute value out of this. They are already ordered from the smallest to the largest absolute difference. So this is the rank. It goes from 1 to 8. This is the sign. Where data go down, the sign is -1. In other cases, it's +1. And this is the contribution to the total statistic, Si times Ri. The sum is 30. The purpose of ranking is that pairs with largest change, like this one here, have more contribution to the test statistic than pairs with small change, like there. And in this figure, we can see how it works depending on how the two samples are located with respect to each other. We can start with the case where all mice lose weight, all lines are blue. In this case, the statistic W will be at its minimum. If you start shifting this sample, shifting this up, and you add more and more to this, the W statistic will increase and it will reach 0, where half of the mice lose weight and half of the mice gain weight. This is a symmetric situation. And then again, it will keep growing until we reach a situation where all mice put weight on. We can build the null distribution in the usual way. We take a population of mice, regardless of the distribution, select a pair of samples of the same size as in our original experiment and find W, repeat it multiple times. And this is the null distribution. The points represent the simulation and the red curve represents the normal Gaussian distribution with the known mean and standard deviation. There are equations for the mean and standard deviation. This is the null distribution. It represents all random samples when the null hypothesis is true. And the null hypothesis is that there is no change between before and after. We take our observation, our observed statistic, which was 30, and put it in the context of the null distribution, cutting tail probabilities on the left and right side, and we find a p-value of 4%, which tells us that we can actually reject the null hypothesis and the change after treatment is real. This is how you can do this in R. You prepare your before and after samples, and you call the same function Wilcox.test as it was in the case of Mann-Whitney test, but now you set a parameter paired equals true. This gives you the p-value here. The summary of Wilcoxon signed rank test. It is used for sample of n pairs of data, before and after case. Values can be ordinal. It doesn't matter what the actual values are. Pairs should be random and independent. And the usage of this is to discover change in individual points before and after. The null hypothesis that there is no change between these before and after, or that the difference between before and after follows a symmetric distribution around 0. This is a non-parametric equivalent of paired t-test. It can be used for paired data only, and as in case of all other non-parametric tests, it doesn't work for very small samples. The next one is Kroskal-Wallis test, which is a non-parametric alternative to one-way ANOVA. Let us start first with an alternative formulation of the Mann Whitney test. Mann-Whitney test is for two samples. It's a non-parametric version of a t-test. As you know, the test is based on ranks. The left panel shows actual lifespan data. We then pull all these data together and rank them from the smallest to the largest. So the right panel shows ranked data. The alternative null hypothesis, which is equivalent to the one I showed you earlier, that probabilities of x being greater than y and y being greater than x are the same. The alternative null hypothesis is that both samples are randomly distributed between available rank slots. This is illustrated in this panel at the bottom. The red and blue points are taken from this figure. They are distributed roughly randomly between all the slots. You can imagine a situation where all the blue points will be on the left, all the red points will be on the right. That would break the null hypothesis. If they are equally distributed, then the result is consistent with the null hypothesis. This can be now extended to multiple groups. On the left, we have data from 4 groups of mice: English, Scottish, Welsh, and Northern Irish. And this is the lifespan. And on the right is the same data, but turned into ranks. At the bottom, you see distribution of 4 nations between all the ranks. There are ties. Ties are when you have data points which are equal to each other. For example, these 3 data points, 2 English and 1 Welsh, have lifespan of 0. This is where the mouse died immediately after birth. They have all the same rank. Normally they will be ranked 1, 2, and 3. In this case, we assign them a mean rank, which is 2. These two would have a rank 11 and 12, but because they are equal, we assigned a rank of 11.5 to them. And the same here. This is how we deal with ties. The test statistic for this test is based on the variance between groups, which is found in a very similar way as we did in ANOVA, but instead of values, we use ranks. And we do not need variance within groups. This variance between groups can be directly compared to a random uniform variance, which is theoretically known. And from this, you can derive a test statistic as in this equation. Obviously, you don't have to remember this. As usual, we build the null distribution from a population of mice. We take 4 samples of the same size as in the original experiment. We find our statistic H, we repeat it and build the distribution of H. Again, this is the null distribution. And our observation is here, and it cuts off 4%. So our p-value is 4%. The null distribution follows the chi-square distribution with 3 degrees of freedom, as shown here. So you can use chi-square distribution to find the probability. This is a comparison between ANOVA and Kruskal-Wallis test applied to the same data. These are the original data. This figure shows ranks. ANOVA gives you a large p-value, mostly because it's confused by these outliers, and variance in the first 3 groups is inflated. These variance within groups are very large. In Kruskal-Wallis test, the p-value is 4%. So under our standard significance limit of 5%, we would say, yes, this is a significant result. And this is mostly due to these Northern Irish mice, which have ranks which are typically lower than everything else. How do you do this in R? Very simple. There is a function called Kruskal.test. You provide it with data, which you can download from this website. And there is a formula, lifespan versus country, and it will give you all results you need, including the p-value of 4%. If you ever need to perform a 2-way non-parametric test, a counterpart of 2-way ANOVA, there is something which is called Shearer ray hair extension to Kruskal-Wallis test. This is even more names to remember. Briefly, it replaces values with ranks and carries out a two-way ANOVA. If you ever need this, this is a paper which describes how this can be done. Finally, summary of the Kruskal-Wallis test. The input for the test is n samples of values. Samples are random and independent, and you compare location and shape of these n samples. You don't compare means. There are no parameters here. The null hypothesis is that the mean rank in each group is the same as the total mean rank, or simpler, there is no change between groups. This test is not parametric, so it doesn't care about distributions. Next, Kolmogorov-Smirnov test. This isn't strictly a non-parametric test because it looks at actual values, but it's a test which is not sensitive to the distribution. It actually compares distributions. So I included this in this talk. To perform a Kolmogorov-Smirnov test, you have to find cumulative distribution of your data. Data points are shown here at the bottom of this panel. There are n points, and this is our lifespan of mice. And you build the cumulative distribution starting from the left. You start at 0, and you continue until you encounter the first data point, and you go up one step. You continue, you go up another step when you encounter another data point, and you do this until you reach the last data point, at which point you should be at 1. This will work if you increase your value of the cumulative distribution by 1 over n minus 1. Why is it n minus 1, not 1 over n? Well, this is because there are n minus 1 intervals between n data points. If you imagine 3 data points, there will be 2 intervals between them, one from 1 to 2 and from 2 to 3. This is how you build the cumulative distribution of any data set. And the test statistic is the difference between these two curves. You specifically look for the maximum vertical difference between the two cumulative distributions. This is English and Scottish mice data. These two distributions are shown in different colors, and the maximal vertical distance is 0.42. If you compare English and Northern Irish mice, these two cumulative distributions look quite different, and the maximum vertical distance is larger. That tells you that these two samples are more different than the English and Scottish mice. You can build the null distribution as shown in this example by simulation. The red curve on top of this distribution is called the Kolmogorov function. It was developed by Kolmogorov. It's an analytical distribution, and you can find probabilities in it. And as usual, we take our test statistic, which in this case is 0.42, and we cut off a probability in this distribution would be 25%. The null distribution and our observation in the context of a null distribution. Kolmogorov-Smirnov test is sensitive to both location and shape of data. In the top example, we have two data sets which have similar distribution, but they differ in their location, in the mean. Their treatment is greater than the control. And the two distributions here, two cumulative distributions, are quite different. The maximal vertical distance, the test statistic is 0.67, and the p-value is small. The second case, the central value, the mean from two samples is very similar. However, the second sample has much more variance than the first sample. The two cumulative curves look different. One of them, for the sample with larger variance, is much shallower. The second one is very steep, and the D statistic is 0.5, which returns a p-value of about 4%. Again, Kolmogorov-Smirnov test does not work for small samples. If you have two samples of size 3, there are only 3 possible values of statistic D and 3 possible p-values, 0.1, 0.6, and 1, which is completely useless. Again, you need at least 8 or 10 data points in each sample to perform Kolmogorov-Smirnov test. This in R, you simply use the function ks.test for 2 vectors to compare them. The summary: the input for this test are 2 samples of values. They don't have to be the same size. The assumption is that the samples are random and independent. That means there is no and after data, and that variables here should be continuous. It doesn't work very well for discrete data, so you need continuous data. The distribution, it doesn't matter. So this is a distribution-free test. The usage is to compare distribution of the 2 samples, and the null hypothesis is that both samples are drawn from the same distribution, regardless of the shape of a distribution. It's not very useful for small samples, and as I said, it's too conservative for discrete distribution. This is a comparison of 2 sample tests, the t-test, Mann-Whitney test, and Kolmogorov-Smirnov test. On the left, we have English and Scottish mice, and all the tests give you a large p-value because there isn't really much difference between these 2 samples. On the right, we have English and Northern Irish mice. You can see by eye that they differ in some way. T-test will give you a p-value of 7% because variance in the first sample is very large. So t-test essentially fails to compare them. We have outliers here. Mann-Whitney test gives you 4%, and Kolmogorov-Smirnov test gives you 1%. It's the most sensitive of them because it recognizes that the distribution in the second sample is quite different than the distribution in the first sample. This is a table for you to copy and keep. It tells you which statistical test you should use depending on your data and the goal of your experiment. Your outcome of your data, outcome of your experiment can be a measurement, which is either symmetric or not symmetric. This would be roughly normal or not normal. It could be ordinal data or a categorical experiment. When you compare central value of 2 unpaired groups, you should use a t-test when your data are roughly normal or at least symmetric. Otherwise, use Mann-Whitney test also for ordinal data. And of course, in categorical data, tests are quite different. When you compare distributions of 2 unpaired groups, you should use Kolmogorov-Smirnov test, is probably best, or Mann-Whitney. When you want to compare 2 paired groups, you used a paired t-test for normal data, Wilcoxon signed rank test for asymmetric, not normal data, and the same for ordinal data. In case of categorical data, there is a thing called McNamara test to compare before and after data. When you want to compare 3 or more groups, you use ANOVA or its non-parametric counterpart Kruskal-Wallis test. I added a few more tests you could see in gray font, like Efron, Tibshirani, permutation, Monte Carlo, and Bootstrap. These are beyond the scope of this lecture. It would take way too long to introduce them, but I added a few slides explaining these tests in the appendix. If you want to find out, you can download the slides from this lecture and find this additional information at the end. This diagram might help you making a more generic decision on what type of test to use, depending on the outcome of your experiment. If the outcome of your experiment is a measurement, then first you want to know if they are out of scale values, like strong outliers. If you have them, you should perform a non-parametric test. Otherwise, you ask whether your data are roughly normally distributed. If not, can you transform them to normal? Perhaps you can take a logarithm of your data and make it more normal. In such cases, you should use a parametric test, which is always more powerful. Otherwise, if everything fails, use a non-parametric test. Obviously, if your data are ordinal, then you use a non-parametric test. And if the outcome of your experiment is a category, like a cell stage from a cell sorting experiment or an outcome of a drug experiment, whether drug worked or not, then of course you use a contingency table. This is the appendix I mentioned about. This is about permutation and bootstrap test. I show how it works, how you build the null distribution for this test. I show you a few examples and the null distribution and the p-value, how to obtain this and how to do this in R. Efron-Tip-Shirani bootstrap test, similar examples and how to do this in R. And finally, the comparison of all two sample tests, including both permutation and Efron-Tip-Shirani test. At the end, there is an appendix about Monte Carlo chi-square test with all the details and examples and explanation how it works in R. Thank you. This is all for today.